Hello, I would be talking about explainable AI at scale. Okay, so while there are various successful ways to think about AI at scale, and deep learning being one of them, key formidable challenges for modern AI are its millions of parameters which are less explainable, and secondly, it does not generalize beyond the experiences or the training data that you show. Right? But on the other hand, humans are known for generalization and reasoning, which is the real world human intelligence we are talking about. And well known DeepMind researchers such as Battaglia and colleagues argued in their 2018 paper that combinatorial generalization, which can be explained as constructing new inferences, predictions, and behaviors from known building blocks of information, must be a top priority for AI to achieve human like abilities. And what that means is the structured representation, for instance, objects connected with relationships and their related computations, are key to realizing this kind of human level generalization and reasoning capabilities. Right, so combinatorial generalization can also be thought of as something similar to human cognitive style, where humans learn or understand by drawing analogies and drawing inferences about one domain or concept based on corresponding knowledge about the other. That's how humans learn. And in last few years, there have been many such approaches that are rising up at the intersection of deep learning and structured approaches. And what these approaches all have in common is capacity for performing computations over large set of different entities and the possible infinite relationships between them. And one of the approaches is graph, which we will be discussing a little bit more detail in subsequent slides. But to summarize, combinatorial approach is definitely something which helps explain various relationships and concepts, and also does it at scale because when we talk about combining these concepts, which are only finite in nature, and when we talk about combining them, it becomes infinite knowledge. So, how do you acquire or create this knowledge? That's where this quote from 18th century French philosopher Denis Diderot comes to light, or is very relevant, I would say, is there's only three principal steps to acquiring knowledge, and which is like observing the nature or collecting facts, reflecting on those facts by combining them, and then seeking more knowledge by experimenting on this existing set of combined knowledge. So, what is a technology world or the real world we know that comes closest to implementing these three steps? Or you would say also helps perform computation over these large set of information that you have gathered and combined and kept in a storage. So, moving on, let's see what is the answer to that. And looks like knowledge graph, I would say, comes closest to that philosophy. And I would say it's a game changer because it applies semantics to give context and relationship to data concepts. And it also provides a framework for data integration, analytics, and sharing with that knowledge. I would say think of them as a flexible means of discovering facts and relationship between people, processes, and applications in ways that can give organizations new insights into their world, right? So for this proof of study concept, I use a news category dataset from Kaggle that has roughly 200,000 news articles, their headlines and short descriptions. And what you see here is a sample subgraph created out of that 20,000 articles, which is about Steve Jobs as one of the entities. So the basic unit of knowledge graph is the representation of an entity, let's say here in case a person, Steve Jobs, which is of type, this particular entity is of type person. That is what it means when it says has ontology. And Steve Jobs as an entity is mentioned in two different articles here, yellow nodes, and these two articles are of business type category, right? So we basically have in this knowledge graph that I was able to create using 20,000 articles, has three different type of relationships, has category, has ontology and part of, and has four different type of nodes. So how do we build a knowledge graph? It should be the next question, right? So let's move on and try to understand that. So building a knowledge graph at a very high level, like I described, has to be a three-step process where you collect the facts, then you combine those facts, and then you use querying skills to mine that knowledge, right? And then the text analytics, as we know today, just does the first step, that is collecting facts for us. So while there are so many different text analytics techniques which helps us break down the text data, one of them is NER extraction, other could be TF-IDF, and then once we break down the information, we use that information to do another set of activities which is called text classification, and most of the time we stop at that. So all of this, either you extract information from the text, or you classify or use that information to classify into some type of news article categories or document categories. It's just collecting information, either category information or the entity information, but we never go beyond that, or go one step further where we load this into some sort of a architecture or a structure rather, where this information is connected in such a way which is conceptually or semantically connected, so you can query them meaningfully at scale. Because what happens is, as these connections grow, there could be millions of connections, and there are infinite number of ways you can connect these entities and their categories. So that's what the power of semantic linking and knowledge finding is. And the way I've tried to do that for this proof of concept study is using Neo4j graph database. And all the previous step that happened, which is like the fact creation step, which is NER and classification, happens in Python, and that is what I just referred to as tip of the iceberg, because a lot of stuff that can be done about information connection happens under the water. That's what you see here, right? So let's move on and see what this gives us. What is the kind of information we would be able to gain if we are able to show this in a graph database format. So let's move to Neo4j Bloom, and let's clear the scene, and let's first explore for example, entity network. So this is a parameterized query that I'm going to use here. So I would say, give me the entity network for Apple. So Apple is an entity that is of organization type, I guess. Yes. So Apple is an organization type, and it has these many articles that are associated with entity Apple, or other way to say it's Apple occurs across all these yellow nodes. Those are of article nodes, and these articles have these different categories like entertainment, politics, wellness, all of these, right? So it takes some time to rearrange itself. So once you are able to do that, I would also want to find out, let's say, if Steve Jobs is an entity, which is an entity, I think, in the database, how is it connected to Apple, right? How many articles did they occur together? So that would be another interesting thing to find. So all I have to do is, I don't have to clear the scene, because that way it would not clear the existing graph on my screen, and I can just simply add another graph on top of it and then see if they are connected. That's the beauty of Neo4j Bloom. So it doesn't clear, it would add another graph on top of this graph and show the connection. So let's do that. Entity network for Steve Jobs. Right, so what we are able to see here is Apple and Steve Jobs are connected together in these two articles, right? And both of them are of business type. But if you see, there are other categories in which news categories in which Apple occurs, and they are entertainment, politics, wellness, and black voices. And like I said, Apple is of type organization, right? And then it is connected to Steve Jobs, which is a type person. And then it occurs in these two articles together. So very nice. So this is a subgraph which is part of a much larger graph, which would take much time if I try to populate it here. But let's try to see what other kind of querying we can do. So going back to our presentation, uh, so this is the slide 7, which I was just actually showing you live on Neo4j Bloom. But like I said, Steve Jobs and Apple are connected through the two articles, but they could have been very well connected through another relationship called CEO. If I chose that, when I was building the graph, I could have very well chosen CEO as a type of relationship, and if that existed in the data, and I was able to figure that out from the articles. So it gives you a lot of flexibility. It's not hard code assumptions that you would have to really add in the database. It could be very free flowing ideas, and it is up to you to decide how you want to connect these entities, right? So let's move on. This is another example where I'm trying to find out top person entities that occur in a sports category, and then I would want to understand for the topmost entity which are the co-occurring entities in a certain class. So in this particular example, I'm trying to find out, Tiger Woods being the topmost entity in sports category, which other person entities occur with Tiger Woods. So this is that network, and like you see here, this is again a parameterized query wherein I'm trying to find co-occurring entities of person class with entity Tiger Woods. I can change this person class to org type or any other type. I have like roughly 15 different types that NER was able to identify, and I could find that network of entities, right? So this is another way you can use this loaded information, graph connected loaded information in Neo4j. Let's move on to another results. This is a temporal study that I wanted to understand and see what are the different type of person entities in politics category year over year. So as you see, into 2014, Obama was on top, but understandably after 2016 elections, Donald Trump started emerging as the top discussed or top mentioned entity in the news, the political news category. As you see, the number of mentions for Donald Trump are way higher than Hillary Clinton or Obama in 2014 and 15, which is another interesting insight here, I would say, because probably there was more written about him or more number of articles that were written about Donald Trump. So this is again like basic SQL-like querying abilities that you have within graph database, and the SQL query is SQL-like query that you have in graph database is called Cypher, and it is very easy to use in the sense that you can actually draw out the kind of patterns that you're looking for and then simply count those patterns, right? So I would not go into details of Cypher, but this is the kind of information that you can get from basic querying. Let's move on. So this is more about what entities you already know, and you may want to know more about them in the surrounding network. But what if you do not know about the database, the graph database much, and you want to know what are the co-occurring or what are the communities of influence and which entities occur together in a certain community, or where a tight-knit part of a tight-knit community. There are definitely graph traversal algorithms or graph algorithms in short, which help you determine these communities. And one of these community detection algorithm is Lovain algorithm that we could leverage to find out within politics news category which are the different type of person entities that co-occur or basically occur together in a community, right? So very interestingly, here we find Bin Laden along with all his mates occur on the top. They form a community, and then another community of interest could be Pope and And then last one could be, let's say, Oprah Winfrey and her close-knit community. So while I would say this is roughly a 20,000 data set, a news article data set, which is not very long. Each article is not very long, roughly around 300 to 400 words. But think about it, if you have really large news items or any other type of documents, the power it gives you to explore the kind of entities or the text extraction keywords or phrases. You do not have to go look for them, but these algorithms can find them for you. And like I said, they are not like hard coded assumptions. They basically come out as come out on the top using this graph algorithm. So very powerful capability, I would say, and really helps you understand the structure of each category. That's why I would say I was able to define these news articles into certain categories or classify them into like politics, business. But what are the some of the interactions happening between entities or the keywords or phrases within each category is really explained using these algorithms, these graph algorithms. That's why I say this is explainable AI, real explainable AI, which is happening at scale, because graph algorithms, they run very fast and the querying is much faster compared to any SQL. In most cases, you would not be able to write a SQL, but these algorithms can spit out information that was unimaginable if you are trying to think of load these into some sort of a relational database. Okay, very well. So let's move on. Like I said, there is a vast world out there in terms of graph. I have been only able to scratch the surface here. I have explored the query-based knowledge graph, which like Cypher-based information that I was able to explain. I was also able to get a little bit into graph algorithms, feature engineering, like finding a community, which kind of gives me a feature if I'm trying to tag an entity to a certain type of community. So those are the two things that I've been able to explore in this proof of concept, but there's so much out there. There's graph embeddings and graph neural networks, which can take all the knowledge to a completely different level. So with that, I would like to summarize and say NLP semantic analysis techniques are just the tip of the iceberg. Like I said, you do the classification, extraction, and leave it there, you're not getting much. But if you load them into some sort of a knowledge graph wherein you are giving them context and relationship, it goes a long way, right? And like I said, it's the semantic modeling in this graph eliminates the problem of hard-coded assumptions, right? It's so free-flowing. Whichever way you want to connect the identity is completely up to you, which is a really powerful concept in itself. And then if you are thinking of building any capability around this within your organization, I think that would be that can be done at scale, and it would help you leverage all the fast evolving text data that you have in the best possible way, right? So you do not have to leave your unstructured text data just at text analytics level. You can take it a notch up and then decide how you would want to connect that information that you have gained so far, and then keep extracting different patterns that were earlier unimaginable. So with that, I would like to say thanks, and if you have any question, please feel free to reach out at this email address. Thank you so much.